I'll be talking about building low latency web applications on the Windows Azure platform. And I thought I would start by talking a little bit about what I mean by low latency web applications. Specifically, I mean applications that might have a global user base, and there's an expectation on the part of the user that when they submit a request, they get a response very quickly. And you might do things in a variety of different ways in an on-premises scenario. For example, you might buy a beefy server and then keep adding more resources to that server to continue to handle the load. In Windows Azure, we go the other direction. We scale out because we think it's cheaper, and then we also think that it adds some other benefits, like giving you some redundancy in the case of failures. So I'll be talking about scale out. And these applications are interesting because they often have demanding requirements in terms of computing resources. And so these are not applications that you can just throw together and hope that they'll work. You really have to design them and think about them, measure their performance, and then improve performance over time. And I find that to be interesting. So that's sort of why I was excited to do this particular talk. This talk is similar to a talk that I gave at PDC, but a number of things have changed. So if you saw that, just hold on. There's more to come. I'm going to talk about this in the context of Windows Azure, and I'll assume for purposes of this discussion that most people in the room are already familiar with the basics of Windows Azure, and so I won't be covering those. And then other than that, we basically would take the same approach that we take in the on-premises scenario, and we just translate it to the cloud. But in some cases, it's easier to do because there are some facilities built into the Windows Azure platform that make it easier to get started and get off the ground in solving some of the tricky problems for building these low latency applications. Finally, I'm going to break this talk into 3 parts. During the first part, I'll talk about synchronous and asynchronous designs, and that's sort of an abstract discussion. I'll draw some pictures and explain what I mean. Then I'll talk about managing data access, which is sort of one of the major pieces of using Windows Azure, both between the client and the server and between different components on the server side. And then finally, I'll talk about measuring and improving application performance once you've got it up and running. So we'll begin by talking about asynchronous design patterns. Does anyone want to volunteer the definition of what a synchronous design pattern might be? Yes? A logical flow of steps that go one after another, so that's good. Blocking weights. So that's sort of I think the key piece in that sequence of steps. Whenever there's a wait, the thread that's handling the request will block, and it will not do anything else until that wait completes and the work is done, whatever the work may be. Let me draw a picture to illustrate what I mean and explain why this is not the thing that you want to do. If you've got a web application and it's got a front end, let's suppose that web app has only a single thread for the sake of an example. In reality, you might have multiple, but let's suppose there's just one. And suppose that a client request arrives. Because this is a synchronous design, the thread is going to take that request and it would dispatch it to wherever it needs to go. Let's say that there's a middle tier and perhaps there's some interaction with a data tier. And then while the work is going on, the thread is going to block. And even if there's other productive work that the thread could do, it's not going to do it. For example, another client request could arrive. The thread's going to ignore that, and that client's going to have to wait. Ultimately, the response will come back after some period of time, and the thread will dispatch that back to the original client. And at this point, it can turn around and it can start to service the second client request. So another question for you guys. What is the data structure in this design that's used to track outstanding requests? It's basically the thread context, whether it's in the registers of the CPU or the thread stack. And that thread is only handling one request at a time. And because each thread services the next request only after the first one completes, it means that the thread count is really the scalability bottleneck. So if you want to add additional capacity to this app and scale it, you've got to add additional threads. And it's pretty inefficient if each additional thread that gets added results in only one additional concurrent request that can be handled at a time. Creating a thread is expensive. There's a long path length there. The footprint of a thread is rather large. You've got to allocate a stack, and there are other various data structures, for example, in the kernel responsible for tracking that thread. So this is a design that's really tough to scale. Now, there's this interesting trade-off when you go with an asynchronous design, which I'll describe next. You end up having a little bit more overhead because you have to track a few more things. And so in some very narrow scenarios, it may make sense to retain a synchronous design. But in those scenarios, that's typically, you typically do that if you don't expect to block. If you do expect to block, generally speaking, an asynchronous design is going to be better. So let me show you a picture of an asynchronous design. There's no magic. We're still only going to handle one request at any given point in time. That thread is still sort of a serial unit of execution. But when the thread blocks, it can queue that work and it can continue to handle other client requests at the same time while the first request is underway. So here we are with the same scenario. A client request comes in, the thread dispatches the request to the middle tier, and then instead of just blocking, it's going to put some data into some kind of data structure. So there's some context tracking data structure. The thread will say, here's that first request, and when I get a response for that, I'm going to send it back to that particular client. And then the thread is going to wait for the next useful piece of work to come along. And in this case, suppose that another client request comes in. It will service that client request, and then it will store the context for that client request. And now suppose that the second request finishes before the first one does. It can go ahead and return the response to the client. And then, of course, the other response comes in, and that response gets returned to the client. Now, obviously, there's an explicit data structure that's being used to track these requests. And because threads can handle additional requests while the first one is in flight, the thread count is no longer the bottleneck. And if we add an additional thread, we'll get the capability of handling many more than just one additional concurrent request. So our application scales in a much more graceful way. There's a caveat here, and that is, can anyone identify what the caveat is? Sorry? The context could become the bottleneck. That's right. That data structure's probably got to be thread safe, so you may have contention on it. And there's also just the overhead of manipulating the data in that data structure. So that becomes the next place to focus in optimizing performance of this particular design. It may not be a bottleneck. It may be a bottleneck. So you'll have to be careful about which data structure you choose, and you'll have to be careful about the overhead of introducing that bookkeeping. So that's sort of the trade-off here. So that sort of ends our discussion on the specifics of synchronous and asynchronous. There are two other points I want to make, though, on this general topic. The first is, it does no good for you to take an application and make the front end asynchronous and leave the middle tier synchronous and the data tier synchronous, because your bottleneck will just move directly to the middle tier. You've really got to plumb the asynchronous design all the way through the application. It's like a chain is only as strong as the weakest link. Well, an app is only as asynchronous as the most synchronous part of the application. So that's sort of one consideration. And in Windows Azure, as well as Windows Server, there are a variety of mechanisms that people use to access the data tier. All of these mechanisms provide asynchronous methods, so I would recommend that you take a look at those when you're designing your data tier interaction. And now I want to talk about failures, because in both the synchronous and asynchronous example, we had a request come into a single front-end role instance. That role instance tracked that outstanding request, say, in memory, and then dispatched it to the next tier of the application. Windows Azure is designed to run on commodity hardware. We strip out all redundancy. We don't use RAID. We don't use dual network connections. We don't have dual power supplies. All that stuff is gone because we want to make the hardware really cheap so that we can pass on the savings to our customers and offer them a low price for the compute, storage, network, and other resources that we sell. As a result, because this is commodity hardware and it's not redundancy, we expect that your software will have redundancy built into it, so that if something fails, you can recover from it. And that specifically means that the data that you store in memory and the data that you store on the local disk inside of the VM where you're running is not considered to be durable. The only durable data is the data that you store in SQL Azure or Windows Azure Storage, or the data that you store in your favorite storage service available over the internet, whatever that is. You can, of course, do tricks like replicating data, but that's actually what we do in Windows Azure Storage and SQL Azure, and so we try to take on that overhead, that burden, so that you don't have to do it. What this means is, if that role instance, that front-end role instance, were to die while those requests are in flight, you need to have a strategy for providing the end-to-end service that you'd like to provide to your customer. For example, maybe the client should eventually time out and then retry the request. And sort of network timeouts and retries are a common approach to dealing with failures in these distributed systems where the individual components can fail independently. There's another useful abstraction, though, that Windows Azure Storage provides, which is the Windows Azure Queue. This is a durable queue, first in, first out. You can enqueue messages on one side and then dequeue them on the other, and it has some nice properties as a sort of a communication channel between different role instances. Let me show you an example and explain what it is that I mean. Suppose that I have two front-end role instances, and I've got a Windows Azure Storage queue, and those role instances enqueue work. And let's suppose that they enqueue 3 work items on that queue. These could be client requests, or they could be images that need to be turned into thumbnails, or they could be, jobs that need to be run, whatever it may be. And then we have some back-end role instances that are responsible for dequeuing the requests and processing them. When the back-end role instances dequeues, that message on the queue does not get deleted. It just turns invisible. So if somebody else goes to dequeue, they won't see that, but it's still sitting on the queue. The second role instance also dequeues. It gets the second work item, and that second work item is still on the queue, but it's invisible. You control, and there's a timeout on that invisibility that you control when you set this up, so that after a period of time, if the guy who dequeued the message doesn't come back and delete the message from the queue, it becomes visible again. So suppose, for example, that first back-end role instance crashes while it's processing the first message. Well, the second role instance is still healthy, so it finishes working on 2. It deletes number 2 from the queue, and then it dequeues the next item. It processes that, and then it deletes that item from the queue. And now, after some period of time, that first item becomes visible again after the invisibility timeout. And that other guy pulls it, processes it, and deletes it from the queue. And so what we see here is 2 nice properties of queues. One is that they gracefully handle failures of a role instance because the other role instance can continue to process the messages, including any messages that were only partially processed by the first one. And it's sort of an automatic load balancer. If you've got a bunch of back-end role instances and these jobs are non-uniform in how much time they take to complete, because the back-ends pull the work, they'll just pull the work whenever they're ready. So you'll have a queue that has a bunch of work, and the backends that are ready will take the work, and those that are still busy won't take the work, and so you'll automatically load balance across the role instances in your application. Now, you still have to worry about contention on the queue, and so sometimes people use multiple queues. They like to have queues with different priorities, so you'll have a high priority queue and then a low priority queue. You can do all kinds of things with these queues. The messages on those queues are durable, so even if you have failures, that's okay. Now, suppose that the work items that were queued in this example were requests to debit somebody's checking account. And the first back-end role instance pulls off number 1, and it debits the account, and then it crashes before it can delete the message off of the queue. And then the second back-end role instance, after it becomes visible again, it pulls off number 1, it debits the account again, and then it deletes it from the queue. Well, your customer's not that happy. The only person who's happy is the person who was getting paid, because they got paid twice as much as they should have been paid. You have to design your application in such a way that you can tolerate failures and repeats of the same operations. Specifically, your work items that you process need to be idempotent. If they're executed once, you get the same result as if they had been executed many times in a row. And that responsibility is on the programmer. The truth is, this is a problem that exists both on-premises and in Windows Azure, and it exists in any system where you expect where it's a distributed system and components can fail. There's no magic here. There's nothing, you can use transactions, you can use tricks like timestamps or sequence numbers to make things idempotent, and so that's really how you'll have to design these apps. So this is not about synchronous and asynchronous, but it is a point about the data that gets stored and processed as it goes through your application. Okay. Yeah, sure. So the question... So the question is, can you retrieve items from the queue, modify their state once the work has been done, and then put them back on the queue, tracking the fact that the state that the state has changed so that the next guy won't repeat the same piece of work. You could. I think the problem is basically a race condition between a failure and the update to the queue. So let's suppose you pull item 1 off the queue, you do the first step of the work, so now it's been done. You're about to requeue it and you crash. Right then, that's the point at which you're vulnerable to doing things twice. So you certainly can do that, for example, put items back on the queue or have multiple queues tracking the different states, but I don't think it solves that particular problem. Maybe it solves another problem. The question is, does the queue support invisibility timeouts? By default, you don't have to implement that. That's correct. There's an invisibility timeout on the queue. I don't remember what the defaults are, but it's there, and you just set that setting. The question is, when items were first invisible and then become visible again, how does it affect the order of the work items in the queue? You have to assume that the order is non-deterministic. Yes, the question is, could you get into a position where you have some items on the queue that let's suppose that there are some items on the queue that because it's a malformed work item, they cause your role instances to crash. Could you get into a situation where you've got like a poison message that always causes something to crash and it just takes down each backend that picks it up? That is a real scenario. That does happen. There is a mechanism to deal with poison items on the queue, and so you can read about that in the queues. I believe that you can retrieve each time that the item becomes visible again, there's a counter that's increased on the item, so you can see if an item is poisonous, and then you can sort of set it aside and deal with it a different way if you'd like to. Any other questions? Yeah. The question is, suppose that the time it takes to process a message exceeds the invisibility timeout, and you know that it's going to exceed the invisibility timeout. Is there a way to notify the queue that the message should not become visible because you're dealing with it? I don't know the answer to that question for sure. Off the top of my head, my hunch is that you can probably tell it that, that the item should remain invisible for another interval, but no? Okay, I'm hearing no from the audience. I'm hearing this is so I assume that if the answer is no, that really the guidance ought to be just set your invisibility timeout to be long enough that you'll never end up in that situation. I know that's not a great answer. So why don't we table that question and we'll come back to that at the end. We can pull up the documentation and double check it. I don't want to give people the wrong information. Then there's another question, which is the invisibility timeout per item or per queue? I believe it's per queue, but it sounds like there are people in the room who will correct me if I'm wrong. Per item. I'm wrong again, so there you go. Thank you for teaching me during this session. Okay, let's move on to the next section. Obviously, this is interesting. Maybe there's a topic at a future conference about sort of building highly available services in the presence of failures. I think there's a lot that could be discussed there. Okay, next I'll be talking about managing client data access. So there are a whole bunch of different kinds of data that you might transfer between the client and the server, and a bunch of different scenarios between the client and the server. And each scenario and kind of data has its own particular trick that comes along with it to optimize the performance and reduce latency. And so I'll just go through a bunch of these different tricks. The first one is a very simple trick. Suppose that you've got a client and you've got some static content that you serve from a hosted compute service. And the way that you've implemented this is that the client goes to your hosted compute service, the hosted compute service turns around and pulls the content from blob storage and then sends it back to the client. Well, the best thing you can do is just get out of the way. By sending the client directly to blob storage, you will be able to take advantage of this highly available low latency storage service that we have that's really scaled out, and so you get much better performance and reduce latency by sending your clients directly to blob storage. And this works great when you have data that's public static content, images, video, sound, binaries, whatever it might be. So that's sort of the first trick. And then you might say, what about content that's not public? What about content that's owned by somebody? Like it's the user's own content, or maybe it's paid content. You know, they've got to subscribe to your service to listen to the music. Or maybe it's content that's free, but it's ad funded. So you'd like to make sure that your users view an ad before they see the content, and you don't want people to be able to deep link directly to the content and bypass your revenue stream. So in that case, there's something called a shared access signature that Windows Azure provides that makes it possible to kind of, with low cost, allow customers to directly access blob storage without opening up that data to the world for them to view. And so what a shared access signature is it's basically a URL that's signed that says the holder of this URL is allowed to access this particular piece of data with these rights during a specific time window, or even for in perpetuity, but your service has the ability to revoke that access whenever you decide that it's appropriate to revoke it. Let me show you an example of how this works. Suppose that I've got Bob, and I've got a service, and I've got blob storage, just like I had before. But instead of having public content in blob storage, I've got non-public content. I've also got the storage account key available to my service. Perhaps I encrypt it, I put it into one of my service configuration settings, and then I've got a certificate that I use to decrypt it at runtime. I never store it on disk in decrypted form, so that key is relatively secure. You can sort of be arbitrarily paranoid about this if you like. And Bob comes to the service and says, hey, I'm Bob, and I want X. And the service has to make two decisions. The first decision is, are you really Bob? So you'll authenticate Bob, and then you'll decide, is Bob authorized to see X? And based on those two decisions, you might make those decisions, for example, using the access control service, sort of as a federated identity provider. You can go ahead and prepare a shared access signature for Bob to see X for a certain time window. And that shared access signature is just a URL, and it says, whoever presents this URL is allowed to access X during time, between time A and B, signed by the storage account key. Your service does not need to talk to blob storage to construct this URL. You just use the functions in the storage client library to construct the URL. It automatically signs it, and then you transmit that shared access signature back to Bob. So far, nobody's talked to blob storage. This has all been done between Bob and your service. And that's a relatively lightweight transaction that just happened. Now Bob turns around and presents that shared access signature, he just does a get on that shared access signature URL, and blob storage takes a look at it and it says, okay, I've been given this URL. Is the signature valid? Yes, it is. Okay, now let me look inside and see what rights that URL grants, and it grants the caller the ability to read X during this time window. The time window is valid. Okay, I'll return the content to Bob. Now, because the shared access signature doesn't identify Bob as the caller, it just says this is the caller, you have to worry about Dr. Evil sort of off on the wings. If Bob turns around and gives that URL to Dr. Evil is going to be able to read the data out of blob storage during that time window. So you have to worry about leaking that shared access signature, which is why we recommend that when your service transmits it back to Bob, you send it over a secure channel so that an eavesdropper won't be able to sniff it and then use it. And by the way, perhaps it's not just for read. Perhaps you'd like Bob to be able to upload images to your service, but not completely flood your service with too many images or really large images. You can actually use this for write access as well, and you can say this person can write to this container for this period of time. And Steve Marks has a great blog post that sort of shows you some sample code for doing this. And so, this deck will be available, so feel free to browse to Steve's blog if you're interested in shared access signatures. And these are really useful. You can use them all over the place. So this allows you to get out of the way between your user and blob storage for non-public content. Now you might say, this is great. I've now got my users going directly to blob storage, but what if my blob storage account is in Northern Europe and my user is in Brazil? That's not a great experience. I'd like them to have low latency, because that's the kind of application that we're building. So it ends up that Windows Azure is equipped with a content delivery network. It's very easy to enable for your storage account. And then that content delivery network will enable you to serve content from the edge. Let me show you a picture of how this works. Suppose that we've got 2 users in Brazil. And what we do, and we've got a public container in Northern Europe in blob storage, and those Brazilian users want to access this public container. We've also got a content delivery network, and that content delivery network has what are called points of presence around the world, little deployments inside of internet peering stations where there's lots of bandwidth and where there are many ISPs that come together. And we locate the nodes in the CDN just a few hops away from the user, even if the source of the data that's going to be served by the CDN is located many hops away from the user. Those hops might be slow, they might be lossy, and so we can provide much better quality of service to users when we're serving close to them than we can when we're serving from some central location. So the first user says, okay, I'd like to get that particular blob. I'm going to use a domain name, and there's some DNS trickery that causes that domain name to resolve to the closest point of presence. So it resolves to some Brazilian point of presence. And that Brazilian point of presence is sort of like a cache at the edge that can hold public content from blob storage. And so that cache says, this user just asked me for this blob. Do I have it? And I'll say, no, I don't have it. I have to turn around and get it from the source. So the point of presence goes to blob storage and retrieves the content once, and then puts it in its own local cache. And the blob header determines how long that item lives in the cache before it's evicted or expires. And then that local point of presence serves the blob to the Brazilian user. Now, if you think about it, this first Brazilian user who requested the blob when it wasn't in the local point of presence actually got a worse experience than he would have gotten if he'd gone directly to the source, because he went, there's another level of indirection. He went to first one place, and then that place went to another place, and then it served it back to him. So the first guy got a bad experience, but the second guy gets a great experience, because the second guy resolves to Brazil, and Brazil gives him the data right away. And every other subsequent user who wants to get that content using the special DNS name that resolves to the closest point of presence will get that fast experience as opposed to the slow experience. And so this is really great if you've got public content and you expect that content to be read more than once in a region between the time that the content comes into existence and the time that it expires from the cache. If you only expect it ever to be read once, don't do this. But more than once, it's worth it. And it'll do a couple of things. It'll actually reduce your cost because you'll pay less for the bandwidth between the Brazilian guy and the Brazilian point of presence. It'll reduce the load on your central storage account, and it'll reduce the latency for your users. And the beauty of these cache control headers is that they're also respected by all of these other caches out on the internet, like corporate proxy caches and like browser caches. So in some cases, you'll be served even closer. Your content will be served even closer to the user. You won't even know. You won't even get billed for it. It'll just work. So this is a kind of a nice approach. Let me talk a little bit more about the CDN, because some of the things are not obvious. Today there are 24 some odd points of presence around the world. And it's extremely easy to enable CDN access for your blob storage account. There's a button that you click in the portal. It generates a new URL. So you'll get a URL that's kind of ugly. It looks like this. AZ, and then a 4-digit number, and then VO, msecnd.net, and then whatever the path is to your blob, you would just append to that at the end. And so you have the source URL, And if people access the source URL, they will always go to the source. And if they access the CDN URL, they will always access that data from the closest point of presence. That first one is the one where there's trickery. Now, you might not like this name if people are browsing your website and they happen to mouse over a link and they see this AZ blah, blah, blah. They might not like that. So we support CNAMEs. Steve has a useful blog post also on setting up the CNAME to work with the CDN. And the biggest problem that I've heard about from people is that they don't like using the CDN because it doesn't support smooth streaming. And smooth streaming is really important for them for their client experience and also to reduce their costs. In fact, we will soon be supporting smooth streaming. So that is sort of the biggest blocker, and that'll be going away very soon. Now, I mentioned that there's a time to live, a blob header that determines how long the thing lives in the cache. And that introduces this interesting trade-off. Will the CDN serve stale content? Maybe. So you've got a trade-off between the staleness of the content and the lowest latency experience that a user can get. And in fact, there's a way around this. But before I describe the workaround, let me just describe exactly how these cache control headers work. By default, when you request something through the CDN, it pulls down the data from the central storage account and it caches it for up to 72 hours. It might not cache it for the full 72 hours. It might decide to evict that item from the cache if it's really busy and it's got to pull something else in. But it certainly won't keep the item for longer than 72 hours. And then it'll go pull it again once that 72-hour time window is up, the next time that somebody requests it. And so you can just set this cache control header. The value is in seconds. I hope you don't set it to seconds. I hope you'll set it to at least hours, if not days or weeks. Really, you want it to be set to weeks to provide the benefit to your users. And of course, that applies to the downstream caches too. So you'll get an extra bang for your buck when you do things this way. And then you're saying to yourself, weeks, how am I going to make that work if I've got an RSS feed of, say, news items? If it's a couple hours old, it's really stale. So how am I going to make that work? Well, there's a trick, and the trick is to use versioned URLs. Let me show you what I mean. Suppose that I've got a blob, my company's new logo, and I want to serve it through the CDN. Well, when I name that blob, I'll put the date into the name, and that'll be the blob that I put in blob storage. And then my HTML that references that blob will have the date in the name. And as soon as my customer goes to retrieve it, it'll get cached in the CDN. And then, a couple weeks later, I decide that first logo was pretty unpleasant. I want a new logo that's going to be prettier. And I set the logo cache control for say, multiple weeks. And I really don't, because I didn't expect it was going to change, and I didn't want to have people have a poor experience accessing my website around the world. So now it's going to be stale for a couple of weeks. So what I'll do instead is I'll put the logo with another date stamp in the name, and I'll change my HTML. And even though that old logo stays in the cache for weeks, the new one will be brought in because that's the one that customers are going to be asking for. And so what I've gotten here is I've got a time to live that's really long, and I'm never serving stale content because I'm using versioned URLs. It's kind of nice when you work with Windows Azure because there are a few situations where things really align nicely. You get lower costs, better performance, and reduced load on your central storage account when you use the CDN. That's one place where everything sort of aligns. Another place where everything sort of aligns is here, because this is really nice both for A/B testing and for easy rollback. If I don't like my new logo, all the old stuff is there. All I have to do is just switch my HTML, and the stuff's already cached, and the stuff's already in blob storage. I don't have to go back and change everything. So I've got a lot of flexibility by doing things this way. Question? Do you pay for the stuff in the CDN? Yes, you are billed for CDN usage. Yep. Question? If you're using the CDN for the HTML, then the only trick, well, so there are two tricks. The first trick is wait 2 slides and I'll explain it. And then the second trick is you can actually write an intelligent client that understands the naming convention that you use for the data that you store in your blob, and it can sort of try to fetch versioned URLs, v1, v2, v3, v4, v5, v6, and it'll fetch all the way up until it gets a 404, and then it backs up to the previous one, and it says, okay, that's the latest one. Well, what I'm saying is there's no, so 2 slides from now I'll talk about the trick there, but if the HTML page is the only way to sort of magically make all of this work if you want to cache the HTML. If you don't like my next trick that's coming up, is you have a smart client. It wouldn't really work for HTML, but it might work for, say, an installer or some other sort of rich client software. So there are ways to do it, but you wouldn't automatically get that effect. Ultimately, it's true that if you have a user in one place and some data in another, they're going to probably have to make at least one long request before they can use short requests. But let me get there. Sometimes people say, well, this is great for static content that I want to serve from the edge, but what about dynamic content that I want to serve from the edge? So what you can actually do is you can now put the CDN in front of a web app. So if you've got a web role that generates HTML, you can just point the CDN at that, and as long as it's stable, that is, it's dynamically generated, but it's not changing every single time you go get it, that can be cached. And so you basically just do the same thing. You have your web app with its source URL, and then you have the CDN URL that points at the same thing, and it'll be served from the cache, except instead of going to blob storage, the point of presence will turn around and go to your web app to get the content. Except it doesn't get it from exactly the same URL that your customer would visit. We actually have you insert this little CDN prefix in there. And people have told us that that's kind of annoying, so we'll work on getting rid of the need to have that. But today, that's how that CDN thing works. You can use CNAMEs. You can use HTTPS. You can also decide whether or not you want the query string in your URL to be used as part of the key that's used to index the cache. And again, Steve has a great blog post on this. Everything that I like to talk about, Steve's already written about, so it makes it easy for me. I don't have to show any code samples. I can just... So this is sort of one answer to your question about how do you do it for the HTTP itself. But then you say, well, what about content that's not stable? It's dynamically generated and it changes every time because I want to provide a dynamic experience to users. Well, then your only solution is really to have multiple services deployed at different regions around the world and to direct your users to the best matching region. And Windows Azure recently introduced a CTP of something called the Windows Azure Traffic Manager, which is designed specifically to allow you to direct your users to the right service. Just like we do when users request something through the CDN, we send them to the closest point of presence. Here we can send them to the closest hosted service. So let me describe how this works. And by the way, this works for non-stable dynamic content. It also works for writes. So it's one thing if you want to just read stuff, but if you want to write stuff, you'd like the destination of the write to be local to your region. So you can use the Windows Azure Traffic Manager. Let's suppose that you have multiple instances of your service that you go provision through Windows Azure at different subregions around the world. And then you've got a user who comes in with a particular IP address. You use a special DNS name that points at our traffic manager. And our traffic manager makes the decision based on a policy that you configure and based on some monitoring data that you also control to send that user a particular DNS response that will then point them at the service that's the best match for them, according to the policy and the monitoring data as we know it at the time. You can use CNAMEs, so it's kind of a funny name, but you can set it up to look perfectly normal. And you might use this for a variety of reasons. Of course, low latency is one, but perhaps there's a tax implication of which data center you send your users to. So you want to send the users in California to the data center in another state, and you want to send the people in another state to the data center in California so nobody has to pay sales tax or whatever it may be. Or maybe you really do need them to be in a particular data center. So you can do this based on sort of the region for tax purposes or compliance purposes. Perhaps you've got a business continuity concern, like you'd like to send people to your US data center all the time, but if the US data center disappears, you'd like to send them to the data center in Europe. Or maybe you just want to give them the lowest latency experience and you'll send them to that place. Also, you might say, well, I just want to send people around the world and balance the load among my data centers. I don't really care about latency. You can do that kind of stuff too. So you configure the policy for whatever goal you have. And although there's one piece that's similar to the CDN, which is this DNS name resolution that points at the best region, this is not otherwise not at all similar to the CDN. We're not serving anything from the edge. We're still serving this from those data centers around the world that, that you can deploy your hosted services in. And the only thing that's cached in this case is the DNS response that goes to the client. So how do you set this up? Half of the stuff is configured by Microsoft. The half that Microsoft is responsible for is we maintain a geo-IP database, so we know which regions the different IP addresses are in. And we take periodic performance measurements from different places around the internet to identify which destination is the best match if we'd like to optimize performance. You control the policy, and we have 4 policies. I think the CTP has 3 policies, but the final version will have 4. Performance, failover, just target people at the particular geo, or just have some ratio for global load balancing around the world. And you also get to configure how we monitor. So we have this monitoring facility in the traffic manager. You've got your multiple services, and you tell us what resource you'd like us to check. This resource might just be, you know, the root directory of your website, in which case that's what we'll try to get. That would be a pretty basic thing to monitor. You might create a page that simulates a synthetic transaction through your service, so it actually exercises the entire service, and you could point us at that as the piece that you'd like us to monitor. And then what we'll do is we'll issue periodic gets, I think it's every 30 seconds, to each of the services that you've configured in your traffic manager policy. And if those gets succeed, we'll keep those instances in rotation. And if those gets fail, we'll take that service out of the rotation. And so the monitoring data plus the policy data determine where you go. Now, as I mentioned, this is in CTP. So there are a variety of things you should be aware of. There's no SLA, there's no billing yet, but please feel free to try it out and see if this works for you. And this will be one of the ingredients that you can use to solve that HTML problem that was brought up previously. That brings us to the end of managing data access between the client and the server, and now we switch to talk about managing data access between the different server components. And the first thing that I'd like to talk about here is in-memory caching. It's often the case that applications have some class of data that's very hot. All of the different role instances are going to access that data. And if that data is stored in the data tier is going to be overloaded with requests for this hot data. And so all of those role instances will be contending with each other to get that hot data. And so a technique that people like to use, and by the way, the technique is they like to cache that data in memory instead of going to the data tier. This doesn't work for every single type of data that your application might handle. It's useful for immutable data, like a catalog of the items on your website that you sell, because it changes very infrequently, so it's easy to cache it and give people a good experience. And it also works for data that's only modified by one user, like a shopping cart. It's not like some other users modifying my shopping cart when I'm shopping on the site. So you'll have to identify the classes of data that are amenable to in-memory caching, and then you can use in-memory caching as a technique. And then what you might do is if you've got your hosted compute and you've got your data tier, you can place an in-memory cache between the compute and the data tier, and that in-memory cache will handle the load. You won't have any disk I/O there. It'll scale very gracefully as you have many simultaneous requests for that hot data. And your data tier will be much less loaded, so that the data access that actually does have to go through to the data tier will perform much better, because there won't be this background load of constantly reading that hot data. And it also actually can reduce cost. If you think about storage transactions, for example, against a Windows Azure storage table, if you're able to cache that data in an in-memory cache, you won't actually be going to Windows Azure storage, so you won't be doing those storage transactions, so you won't have to pay for them. So this is another place where both cost and performance line up to push you in the same direction on Windows Azure. Again, a nice thing. Now, there's something called Windows Azure App Fabric caching, It's a service. It's actually an in-memory distributed cache that we host and run and administer on behalf of all of the people who want to use it. You pay for the service, and depending on what you pay, you get caches with different levels of service and different capacity. It's very similar to the Windows Server App Fabric cache that you could install on premises. They're not exactly identical, but there is a roadmap for them to be identical, at least in the respects in which it makes sense for them to be identical. So you can write an app once, and it can actually use either one of these infrastructures. It's really got excellent performance. It's scalable. We have instances of the caching service in each of the regions around the world, so your cache is very close to where your hosted compute is and where your data tier is, so you don't have that latency across data centers. And we make sure that that cache is highly available. There is authentication because this is done over the network, and authorization that's done through the access control service. When you go to provision this, you get this key that you just plug into your config, and then it works, and that authorizes you to access the cache. And you can imagine that the set of policies for access that we could provide will become richer over time because the access control service is pretty flexible. And you don't have to use ours. You can use your own. If you'd like to use Memcached, for example, you can. It works with Windows Azure. In fact, there's a solution accelerator for it. But I will try in the next slide to convince you that App Fabric caching is a better choice than Memcached. So the first thing is you don't have to manage Windows Azure App Fabric caching like you would with another option. It's already there. It's a hosted service. We manage it. We provide it. You don't have to pay for the compute hours that you would spend hosting that service. So it can be nice that this is just available. Also, the integration with App Fabric caching is extremely easy. There's an ASP.NET output provider and an ASP.NET caching provider, and you just drop those into your web config, and then it lights up and it speeds up your application. So it's extremely easy to do. And if you're one of those people who has an on-premises app that uses Windows Server App Fabric, you can then use that same code and you just compile it against the cloud. You don't have to change anything, and it works in the cloud as well. So this is one of these nice portability stories between on-premises and Windows Azure. And then the other really nice thing about App Fabric caching that is not present in Memcached is this idea of a near cache. So the libraries that provide the interface to the distributed in-memory cache implement a local cache in memory on the client side. And the hottest data will live in that local cache, and it's not even serialized, so this is extremely fast. And so your hottest data will actually get the best response time, and that's something that's unique to App Fabric caching. Okay, the last topic having to do with managing data transfer on the server side is the topic of SQL Azure sharding. I just want to give a disclaimer before I get into this and say I'm not an expert on sharding. So what I'm about to show you is not nearly as sophisticated as what you can learn from, say, Lev Novik, who gave a great talk at PDC on sharding. So that's where you should go to get the real dirt on sharding. But I'll give a quick overview of this. The idea of sharding is that if you've got a SQL Azure database, and actually the same thing applies really to any database, you can take that database and you can partition it or shard it according to some scheme that makes sense given your workload, and create multiple separate databases that you can then access in parallel. And those separate databases will give you better performance than if you had one big shared database. And again, it depends on your workload, and it depends on the partitioning scheme that you come up with. So for example, a very bad example, something not to do is if you have a database with all of your users, A to Z, you could create two different databases, A through M, and then through Z. Your application would know what your partitioning scheme is, so it can send the queries to the right database depending on which user they're associated with. And so that is useful for a few different reasons. SQL Azure today has a 50 gigabyte size limit, so if you want to go above 50 gigabytes in SQL Azure, you would have to shard. That's your only option. The other thing is that we run on this commodity hardware. This is not big iron. And if you've got a database load that is, you traditionally run on big iron, we really recommend splitting that database into smaller pieces because you're going to get better performance out of the hardware that we run on in Windows Azure. Now, even if that were not the case, I would still go around recommending sharding because it speeds up database performance regardless of what your scenario is, as long as you don't have to do a lot of sophisticated operations, like relational operations across those multiple databases. As long as your operations are confined to the domain of individual databases one at a time, you can do pretty well, and you can actually parallelize your work across all of those databases and across all the hardware that we take advantage of. This same technique ends up being relevant for Windows Azure Storage Tables as well, because Windows Azure Storage Tables require that you designate a partition key, and then each partition, we're able to load balance across those partitions. We're able to do transactional batch operations against one partition at a time, but not across multiple partitions. And so Jay Haridas gave a talk on Windows Azure Storage, I believe, yesterday. And so that's the place to go to learn more about, or today? This morning. I'm getting everything wrong today. Thank you. The talk was this morning. And so he talked a little bit, I think, about partition keys. The partitioning scheme will vary depending on the data set that you have. Would anyone like to tell us why the partitioning scheme that I have demonstrated here is not a good one? Yes? Everyone's name is A. So it wouldn't be spread very, very well. Yeah, the comment is if you can have both logical partitions and physical partitions, then you can make the decision to split multiple physical partitions when a particular logical partition gets hot or overloaded. And if you have to introduce new logical partitions, it requires changes to your application, and it's rather heavyweight. So one option, for example, is you could hash the name of the user, or perhaps you have one lookup that tells you the date on which the user became a user of your service, and then you have a temporal partition by date. And as that scales gracefully over time, because you can keep just adding new partitions on the end once the previous one gets full. So sharding, again, is kind of a deep topic. I'll leave it to the experts on SQL Azure to give you the full rundown on that. Finally, we move on to performance tuning. This is probably the most straightforward part of the talk. And so I'll talk about some basic performance tuning and then some more advanced performance tuning. And the trick here is most of this is exactly the same stuff that you would do on Windows Server. There's really almost nothing that's special for Windows Azure. Specifically, what I mean by that is don't just go try to tune performance willy-nilly. You really should measure and observe where your bottlenecks are and then address those bottlenecks and move on to the next thing. But I will say one of the nice changes that we made this fall is that we switched from hosted web core to full IIS in Windows Azure. And what that means is if you're used to tuning performance on Windows Server, you can do all of the same things that you do on Windows Server in Windows Azure now. It didn't used to be the case, or you had to go about doing it in some strange way. So any setting that you'd like to modify, you can do so. People have created these startup tasks that use the web platform installer to install IIS extensions that improve their performance. They use app command to configure IIS, so that way, let's suppose a node dies, your role instance is migrated to another node, that node is brought up for the first time, you'll automatically get IIS configured with the right set of settings. Another set of basic tips, don't build in debug mode and put it in production. You'll get much better performance if you build in release mode, and don't enable IntelliTrace in production. It's really just intended for dev time debugging. Failed request tracing is sort of interesting. Some people like it on in production, some people don't. There are a variety of different settings that can actually introduce significant overhead, so you should just use that when you need it. Now the thing that's unique to Windows Azure is that we provide this scale out mechanism, so you can add role instances whenever you need them, and in fact you can do so dynamically. There are service management APIs, so you could measure queue lengths or response times or whatever it is that determines the load on your application, and you can add additional role instances dynamically. And Sriram Krishnan gave a talk, I think 2 years ago, where he demonstrated this. And so you can find that. We can talk about it. I can point you at that if you're interested. So that's sort of the basic set of tips. The more advanced tips, something that people often forget to do is by default, compression is enabled for a variety of content types, but there are a few that are not enabled by default. JSON is one of those, and then the Office document formats is another, so I recommend going and checking that out. You'll have a little bit of a trade-off between bandwidth usage and CPU usage. Typically, enabling compression is the better choice, so benchmark it and see which is better. The next thing is there's this application recycling timeout. You can tune that now that we're on full IIS. Steve has a great blog post on exactly how to do that. Some people value this because they have memory leaks in their application, and this sort of sidesteps the memory leaks and causes you to reclaim those resources. I wouldn't recommend that. I think if you've got memory leaks, you've got to treat it as any other bug and diagnose it and solve it, because it will affect your performance between recycles. Finally, there's one Azure-specific piece, which is that there's this ASP.NET cache that by default is not on the resource disk, so the size of that cache is limited. You can actually move it to the resource disk using app command, and then you can make a much bigger cache if that will optimize your workload. And then, of course, there's Windows Azure Diagnostics that some people use to collect data, counters and traces and so on from their role instances running in the cloud. And one of the nice features of Windows Azure Diagnostics is that it allows you to dynamically change the data collection settings at runtime without redeploying your application. So use that to your advantage. In other words, maybe buffer just a small amount of data locally, just the most urgent events, let's say, and then upload those on demand when you need them, as opposed to constantly uploading all of your verbose information, because that will also improve your performance. When we talk about performance tuning, and I don't have a slide on this, one of the interesting issues is load testing. How do you load test? Because if you're load testing from your on-premises client, you're probably going to be limited by the network bandwidth between you and the Windows Azure Data Center. So then what people do is they end up putting load testing clients into Windows Azure sitting next to their production service and point those load testing clients at their production service. And you can drive a ton of load from worker roles that just hit a URL. And you can actually log your results into Windows Azure Storage or into SQL Azure, and that's a useful way of load testing what it might be like. And some people like to put their load testing clients at different regions around the world and point them all at a particular service in one region, and that's also another way of testing load. Now, in some cases, you might observe throttling, and if you do see that, because we might believe that there's a DOS attack underway against your service, if you do observe that, call us up and let us know, and we can disable that so you can do your load testing the way you like to do it. So let me just recap what we've talked about. We started off with this synchronous hosted compute service. We made it asynchronous. And then, instead of sitting in between public static content, we got out of the way, and we had our users go directly to blob storage. We also did the same for private static content by using shared access signatures. And then we introduced the CDN to serve public content from the edge, both from blob storage as well as from our web app. And we used versioned URLs and the cache control header to make sure that we have long-lived cache items without serving stale content. We also added multiple replicas of our service at different data centers around the world, and we used the traffic manager to direct our users at the best match. And on the back end, we inserted an distributed in-memory cache between our mid-tier and our data tier, or our web tier and our mid-tier. And we also sharded our SQL Azure database. Finally, we went back to our application and we measured and tuned the application to optimize the performance that we observed. And hopefully, we ended up with a low latency web app. Most of the things that I've shown you here are exactly the same sorts of things that you would do on premise. So there's nothing magically new here, except that the Windows Azure platform offers a set of pre-configured services and facilities that we view as sort of core parts of a cloud operating system that make many of these things easier so that you can focus on your business as opposed to having to focus on the same tasks that every single service owner needs to solve around the world. Thanks very much. I'll take questions. Yes? Does the shared access signature introduce extra latency if a client uses it to access blob storage? I guess I can imagine two ways that it introduces extra latency. The first is that in order to get the content, it's first got to go to your hosted compute service to get the shared access signature, and then it's got to go to blob storage as opposed to just going to one place. So there's some risk that that shared access signature would introduce latency, especially for content that's really small. The question is, if you get 100 small files, you only get the signature once. So it depends. You can configure the shared access signature to give access only to a single file, or you can give access to a container. And if you give access to the container, it grants everything. It can grant access to everything underneath. So you can tune that for your specific scenario. And then, of course, Windows Azure Storage, I guess it has to validate that the signature is well-formed and so on, and that the date range is valid. But that's going to be, just drops in the bucket compared to probably the network latency. Yeah. How does using the CDN drive down your costs? Yeah, you don't. So I believe that with the CDN, you only pay for bandwidth usage. You don't pay for storage transactions. You pay for each location that it's served from, but you don't pay storage transactions against your central Windows Azure storage account. So suppose you had a blob, and suppose you had somebody get that blob 1,000,000 times. Well, if you're not using the CDN, you're going to have 1,000,000 storage transactions. And let's suppose that it gets cached at 3 edge locations, but then those 1,000,000 requests go through those edge locations. You're only going to pay for 3 storage transactions. So your costs on Windows Azure Storage are going to go down. You'll also, it really has nothing to do with the CDN per se, but by setting that cache control header, you'll also allow browser caches to cache the blob and proxy caches to cache the blob. And if it's served out of those caches, Windows Azure won't even know. So you'll save money there too, both on bandwidth and storage. Yeah. Can you set cache headers on the blob storage directly? Yes. There's you can set headers on each blob, and there are tools out there that allow you to do it. You can also call the APIs to do it. Yeah. Does our CDN have any routing performance additions to it like Akamai? I don't know. There's someone who's here named Tina Stewart who works on the traffic manager, and so she may know. So if you come by the booth, we can ask them and find out for sure. I just don't want to give the wrong answer. I've shown you what my track record is on that. Yeah. If you need to get 1,000 small files from blob storage, can you batch them? Well, in a sense you can. If you create a blob that contains all of those files, you could just fetch that one blob. But if they're different blobs, those would be separate requests. Each blob is its own. You'd have a separate get for each blob. Yeah. So the question is, can the CDN be used to distribute private content and still preserve the privacy of that private content. So let's suppose that you pointed the CDN at a, let's suppose that you enable the CDN for your storage account, and then you have a private blob, and so you use a shared access signature to access that private blob through the CDN URL. Well, it'll work in the sense that the CDN will cache that content, but then the CDN won't enforce authentication and authorization on that blob, so anybody could read it. What you could do is you could encrypt your blobs. You could serve those through the CDN. Anybody could retrieve those blobs, and presumably only those people with the key would be able to make use of them. And so you would sort of be implementing a scheme similar to the shared access signature scheme yourself in your own application logic. Yeah. The question is there a way to move the storage close to the users? Let me make sure I understand the question. I think you're talking about the scenario where I have multiple instances of my service running in different data centers, and I want to make sure that the user's storage is located at the same data center as the service that's serving the user. So, okay, so you certainly can do that. Your application could be responsible for doing it. I believe, actually, that SQL Azure has some data sync libraries that are available that you might be able to use to replicate data yourself between those data centers. There's a SQL Azure booth, and they could tell you more about that. I'm not an expert on that.
Yes, we have released actually the data sync service. It is in CDP release at the moment, and it allows you through a management portal to configure actually data sync between different data centers.
And actually, we anticipate that that's going to be really popular for a variety of scenarios, both this scenario as well as disaster recovery scenarios. Yeah. Can you replicate between blob storage locations? You can. You would be doing it yourself. We are working on replication between blob storage locations that would be automatic and then sort of under your control. But we don't have it isn't totally finalized yet, so I don't want to say something that ends up being incorrect. But it's on our roadmap, and it's coming soon. Yeah. Okay, we've exhausted the questions. I hope everyone will please submit feedback. I'd really love to hear what could have been better. I know maybe I can answer questions correctly the next time, so I'll work on that. And I'll be at the booth, you know, on and off today and then tomorrow, so feel free to stop by if you'd like to chat or catch me up here afterwards. Thanks very much for coming.